You look up at the night sky and assume you know what comets do. Red dust, predictable brightening, solar radiation pushing material away from the sun. That is what our comets do. 3. I-Atlas does not play by those rules. First spotted on July 1st, 2025 by the Atlas telescope in Rio Hurtado, Chile, this visitor from another star system has now turned electric blue. Not the faint blue tint you see through amateur filters. Electric blue, bluer than our sun. Third interstellar object ever detected passing through our solar system, and it is rewriting what we thought we knew about comets. The object reached its closest point to the sun on October 29th, 2025. And when space-based observatories caught it emerging from behind our star, something had fundamentally changed. The question is not whether this matters. The question is what this blue shift actually tells us about where this thing came from and what it is made of. July 25th, 2025. Lowell Observatory astronomer Chi-Cheng Zhang and U.S. Naval Research Laboratory scientist Carl Baddams are watching their screens. Ground telescopes have lost sight of 3I Atlas. The comet slipped behind the sun during solar conjunction on October 21st. Earth-based observation impossible. But Zhang and Baddams realized something. Solar monitoring satellites designed to watch the sun's corona can still see it. Stereo, a spacecraft. SOHO's LASCO instrument. GOES 19 weather satellite. All positioned to catch this interstellar visitor during the most critical phase of its journey, between mid-September and late October 2025, as 3. I-Atlas closed from about 2 astronomical units to 1.36 astronomical units from the sun. These instruments captured something unprecedented. The brightness did not just increase, it exploded. Zhang and Baddams published their findings on Archive on October 28th, 2025, in a paper titled Rapid Brightening of 3 I-Atlas Ahead of Perihelion. The data showed the comet's brightness scaling with heliocentric distance to the power of negative 7.5 plus or minus 1. Read that again. Negative 7.5. Most Oort cloud comets brighten following an inverse square or inverse cube law. This interstellar visitor was brightening at roughly twice that rate. Something on its surface was reacting to solar heating in a way never observed before in cometary science. GOES 19's CCOR. One instrument resolved the comet as an extended source. Coma, approximately 4 arc minutes in diameter. A glowing envelope of gas and dust actively shedding material as solar heating intensified. The calculations suggested 3I Atlas brightened to around magnitude 9 by perihelion. Bright enough for small amateur telescopes. Bright enough for thousands of observers worldwide to potentially see this visitor from beyond our solar system with their own equipment. But the color shift, that is where the data gets strange. If you value documented astronomical observation and spectroscopic analysis like this, subscribe. It is the best way to support this work. Also comment from which city you are hearing this from. This script is researched and factual using sources from the Archive preprint server, where Zhang and Baddams published their peer-reviewed observation data on October 28th, 2025, backed by multi-instrument confirmation from NASA's Solar Terrestrial Relations Observatory Stereo AA, the European Space Agency's Solar and Heliospheric Observatory SOHO, and NOAA's GOES 19 satellite, instruments that provided continuous photometric monitoring during the critical perihelion passage when ground-based observation was impossible. Now back to the information. SOHO's LASCO color photometry showed 3I Atlas, appearing distinctly bluer than the sun. Zhang and Baddams wrote this in their paper, distinctly bluer than the sun. For context, our sun is a yellow-white star. Comet dust typically reddens sunlight when it scatters through the debris cloud. Red dust dominated early observations of 3I Atlas back in July 2025, when astronomers like David Jewett at UCLA and Jane Liu, using the Nordic Optical Telescope on July 2nd, confirmed the object was clearly active with a reddish appearance. Spectroscopic observations published by Tony Santana-Ross and colleagues in August 2025 reported the coma had become redder throughout July, indicating dust-rich composition similar to the previous interstellar comet 2I Borisov. Then September arrived. Astrophotographers Michael Yeager and Gerald Riemann captured images on September 7th showing 3I Atlas with a green glow, diatomic carbon emission, cyanide gas. The Very Large Telescope in Chile detected cyanide on August 21st, 2025, and also found something else. Nickel vapor in the coma. Astronomer Thomas Puzia, who co-led that discovery, said it was super exciting. Nickel should not vaporize at the distances 3I Atlas was traveling. nearly 4 times Earth-Sun distance, temperatures far too low. Yet there it was in the spectroscopic data. By late October, during perihelion passage, the color had shifted again, no longer red, no longer green, blue, electric blue. Harvard astrophysicist Avi Loeb published an analysis on Medium on October 30th, 2025, examining what this blue coloration meant. For a natural comet, this blue color is very surprising, Loeb wrote. Dust would result in having a redder color than the sun. The blue shift suggested gas emission was contributing a substantial fraction of the visible brightness near perihelion, not scattered sunlight off dust particles, direct emission from ionized gases. Loeb proposed 2 explanations. It could potentially be explained by a hot engine or a source of artificial light, or it might instead be a signature of ionized carbon monoxide for a natural comet. Carbon monoxide gas, when ionized, emits in blue and ultraviolet wavelengths. The James Webb Space Telescope observed 3I Atlas on August 6, 2025, using its near-infrared spectrograph instrument. Results announced by NASA on August 25th. The data revealed the comet's chemical makeup: 87% carbon dioxide, 9% carbon monoxide, only 4% water. Essentially the opposite composition of typical solar system comets. Martin Cordner and colleagues analyzing JWST's NIR-SPEC integral field unit data calculated emission rates. 129 kilograms of carbon dioxide per second, 14 kilograms of carbon monoxide per second, 6.6 kilograms of water per second. The carbon dioxide to water ratio sat at 8:1, one of the highest ratios ever observed in any comet. NASA's Sphere-X mission observations from mid-August 2025 showed an extended carbon dioxide coma spanning at least 348,000 kilometers in radius. CM Lisa and colleagues published findings and research notes of the AAS Volume 9 on August 21st, 2025, confirming strong water ice absorption and massive carbon dioxide presence. Carbon monoxide becomes the key. When solar ultraviolet radiation hits carbon monoxide molecules, ionization occurs. CO plus loses an electron. That ionized carbon monoxide emits photons in specific wavelength bands, blue visible light. The process intensifies closer to the sun, where radiation flux increases. 3I Atlas at perihelion. 1.36 astronomical units received intense solar bombardment. If the coma contained enough carbon monoxide gas being actively outgassed and ionized, the resulting emission could dominate the visible spectrum. Blue overwhelms red. The comet appears bluer than the sun itself. But there is another chemical process at play: nickel tetracarbonyl. Scientists working with a very large telescope proposed this volatile compound forms in the comet's coma. Nickel carbonyl breaks apart under solar ultraviolet exposure, releasing carbon monoxide and nickel atoms. This industrial chemical process, normally associated with nickel refinement on Earth, appears to be occurring naturally in 3I Atlas. Willem Hugendam and colleagues at the University of Hawaii at Manoa published findings based on Keck Cosmic Web Imager data, collected August 24, 2025. Their paper, currently available on OARSHOV, confirms nickel carbonyl formation. Exotic chemistry unfamiliar to mainstream cometary science. The nickel emissions show another oddity. They extend in both solar and anti-solar directions. 3I Atlas developed an anti-tail, a structure pointing toward the sun. Classic cometary tails point away from the sun, driven by radiation pressure. Anti-tails defy this pattern. Hugendam's team confirmed, as of late August 2025, the anti-solar tail existed in both cyanide and nickel emission profiles. No visible dust tail appeared in white light images. Solar radiation pressure was not driving dust emission the way it drives material in normal comets. Something else was propelling material both toward and away from the solar direction. Davide Farnocchia, navigation engineer at NASA's Jet Propulsion Laboratory, reported non-gravitational acceleration. 3I Atlas was moving slightly faster than gravity alone could explain. Radial acceleration away from the sun measured 135 kilometers per day squared. Transverse acceleration 60 kilometers per day squared. This type of acceleration typically results from outgassing. As volatile ices sublimate, turning directly from solid to gas, they create tiny jets that push the comet. Rocket effect on a cosmic scale. The acceleration direction and magnitude must match the outgassing pattern. For 3I Atlas, the numbers suggested massive material loss. Loeb calculated the implications in his Medium article published November 2, 2025, titled Gravitational Lensing of 3I Atlas by the Sun. For a thermal ejection speed of a few hundred meters per second, the evaporation half-life of 3I Atlas is 6 months. over the month it takes to cross perihelion separation distance, the object would lose about 10% of its mass, 5 billion tons of gas. That scale of mass loss should produce a massive debris cloud. Zhang and Batams noted in their October 28th paper that continued observations during November and December 2025 would be critical. 3. iAtlas was scheduled to make its closest approach to Earth on December 19, 2025, at approximately 1.8 astronomical units, far enough to pose zero impact threat, close enough for detailed ground-based spectroscopy. The blue color shift matters because it reveals composition and activity level. Red appearance in July came from dust scattering, large dust grains several micrometers in size. Hubble Space Telescope images from July 21st, 2025 showed a teardrop-shaped cocoon of dust. David Jewett at UCLA, who captured those images, helped constrain the nucleus diameter between 0.32 and 5.6 kilometers, with most likely diameter less than 1 kilometer. Small nucleus for such dramatic activity. Green appearance in September came from diatomic carbon and cyanide emission. Standard cometary behavior as solar heating increased, but blue appearance at perihelion came from something more intense. Ionized carbon monoxide dominating the visible spectrum. Gas emission outshining dust scattering. That requires extreme outgassing rates and very specific chemical composition. 3. iAtlas fits both criteria. The 87% carbon dioxide, 13% other volatiles mix creates conditions where carbon monoxide ionization becomes the primary visible light source close to the sun. Temperature drives everything. At 1.36 astronomical units, solar flux is approximately 500 watts per square meter. Surface ice sublimates. Carbon dioxide, sublimation temperature around 194 Kelvin at 1 millibar pressure. Water ice sublimates around 273 Kelvin. Carbon monoxide sublimates at temperatures as low as 68 Kelvin. 3I Atlas likely formed in a protoplanetary disk far colder than our solar system's inner regions. Yang Guo and colleagues published a September 2025 study suggesting the comet may have passed within 1 parsec 3.3 light years of 25 known stars in the past 10 million years. Parent star unknown. But the extreme carbon dioxide richness indicates formation beyond the carbon dioxide frost line where temperatures stay cold enough for carbon dioxide to condense into solid ice. Most solar system comets lose their carbon dioxide if they spend too much time near their parent star. Repeated perihelion passages bake off the most volatile ices. What remains is water ice and silicate dust. 3I Atlas preserved its primordial carbon dioxide because it spent billions of years in cold interstellar space, never approached a star until now. The JWST data showing carbon-13 isotope presence suggests this ice has been frozen since the comet's formation. Pristine, ancient material from another stellar system now vaporizing in our sun's heat. The blue shift documents this vaporization in real time. As carbon dioxide sublimes, it carries carbon monoxide with it. Solar radiation ionizes the carbon monoxide. Blue photons flood the visible spectrum. The comet transforms from red dust cloud to blue gas emission in a matter of weeks. Zhang and Batams calculated the brightness increase followed an inverse distance law with exponent negative 7.5. For comparison, most Oort cloud comets follow exponents between -2 and -4. 3I Atlas was brightening 2 to 3 times faster than any well-studied solar system comet at similar distances. Why? 2 possibilities: composition or structure. If the nucleus has unusually high volatile content concentrated near the surface, rapid sublimation produces intense outgassing, thin dust mantle, high ice fraction, fast rotation exposing fresh surface to solar heating. Observations from July 2nd through 29th, 2025, by various ground telescopes measured a rotation period of 16.16 hours with light curve amplitude of 0.3 magnitudes. That suggests an elongated nucleus tumbling in space. Each rotation exposes different terrain to sunlight. If volatile rich patches exist on the surface, periodic outbursts become possible, or perhaps the long interstellar journey altered the nucleus structure. Cosmic ray bombardment over millions of years. Radiation damage creating microscopic fractures. Amorphous ice structures with higher surface area. When solar heating begins, the compromised matrix allows rapid gas escape, explosive sublimation instead of gradual vaporization. Either explanation could produce the steep brightening curve and blue gas emission observed at perihelion. The data does not yet distinguish between them. James Clerk. Maxwell Telescope observations on September 7th and September 14th, 2025, tracked hydrogen cyanide production rates. First observation showed 1.5 times 10 to the 25th molecules per second. Week later, 4.5 times 10 to the 25th molecules per second. Production tripled in 7 days as the comet approached from 2.33 astronomical units. By mid-September, diatomic carbon emission dominated, creating the green appearance captured by Jaeger and Riemann. But cyanide is a minor component. Hydrogen cyanide production 2 kilograms per second, compared to 129 kilograms per second carbon dioxide. The green phase was transitional. Carbon dioxide and carbon monoxide outgassing would overwhelm cyanide emission closer to the Sun. October 3rd, 2025. 3I Atlas passed within 0.19 astronomical units of Mars, 28 million kilometers, closest planetary approach before perihelion. ESA's ExoMars trace. Gas Orbiter and Mars Express spacecraft observed the comet between October 1st and 7th. The color and stereo surface imaging system aboard ExoMars TGO captured images showing the fuzzy white dot moving against the starfield. Coma measuring a few thousand kilometers across clearly visible even from Martian orbit. Mars. Reconnaissance. Orbiter's HiRISE camera captured high-resolution images on October 2nd and 3rd. Congresswoman Anna Paulina Luna submitted an official letter requesting disclosure of those images. As of early November 2025, those HiRISE images remain unreleased to the public. October 21st, solar conjunction relative to Earth. 3I Atlas disappeared from ground-based telescopes. 8 days later, on October 29th, perihelion. 1.36 astronomical units from the Sun, exactly when the blue color shift occurred. Zhang and Badham's photometry from Stereo A and SOHO caught the transformation. 8 days after perihelion. On November 6th, the comet re-emerged into twilight skies. Observers in the northern hemisphere can now track it moving northward through Virgo. Altitude 10 degrees before dawn on November 9th for 40-degree north latitude. Altitude 20 degrees by November 16th. Between November 15th and 16th, the comet glides within half a degree of barred spiral galaxy, NGC 4691. Visual observers with 8-inch or larger telescopes under dark skies should see the blue-tinted coma. The blue color is not a false color artifact. Zhang and Badhams used LASCO color photometry. That instrument measures actual wavelength bands and visible light. Blue channel, green channel, red channel. When they processed the data, blue intensity exceeded solar blue intensity. The Sun appears yellow-white because its spectrum peaks in green-yellow wavelengths around 510 nanometers. Objects reflecting pure sunlight match the Sun's color. Objects emitting their own light can appear any color depending on emission spectrum. 3. I Atlas at perihelion was emitting blue photons in excess of reflected sunlight. That excess came from ionized carbon monoxide gas emission. Live Science reporter Harry Baker published an article, November 4th, 2025, noting this was the third observed color change for 3I Atlas. Red in July, green in September, blue in late October. 3 distinct spectroscopic signatures corresponding to 3 distinct chemical processes. Dust scattering, cyanide emission, ionized carbon monoxide emission. Each phase reflected changing temperature and sublimation rates as the comet approached the Sun. The blue phase represents peak activity, maximum solar heating, maximum volatile outgassing, maximum gas ionization. After perihelion as 3, I Atlas recedes from the Sun, the blue emission should fade, gas production should decrease, dust may again dominate the visible appearance. But the observations during November and December will confirm or refute that prediction. Multiple spacecraft will continue monitoring. NASA's JUICE mission scheduled for November 2025. Observations. NASA's Juno spacecraft slated for imaging in March 2026, when 3I Atlas makes a close approach to Jupiter at 0.36 astronomical units on March 16th. Hubble Space. The telescope will perform ultraviolet spectroscopy in November, measuring sulfur to oxygen ratio and gas composition. JWST scheduled for additional observations in December after the Earth close approach on the 19th. These observations will determine whether the blue emission persists or whether 3I Atlas returns to dust-dominated red appearance. The Vera C. Rubin Observatory. Legacy survey of space and time will discover more interstellar objects in coming years. Pre-discovery observations by Rubin showed 3I Atlas. Coma diameter grew from 13,040 kilometers on June 21st, 2025 to 18,760 kilometers on July 2nd. Continuous monitoring as the object brightened from 23rd magnitude to 9th magnitude. Future interstellar visitors will be detected earlier, tracked longer, studied more thoroughly. 3 I-Atlas is the third interstellar object ever confirmed. 1 I Oumuamua in 2017, 2 I Borisov in 2019, now 3 I-Atlas in 2025. Statistical models suggest one interstellar object per year passes through the inner solar system. Most go undetected. Rubin will change that. Within a decade, astronomers expect to catalog dozens of interstellar comets and asteroids. Population-level studies will reveal how common the 3 I-Atlas composition actually is. That composition remains the central mystery. 87% carbon dioxide, 13% other volatiles. Water accounts for only 4% of the gas emission. Most solar system comets are water-dominated. Water ice, 60 to 80% by mass. Carbon dioxide, 1 to 10%. The reversed ratio in 3 I-Atlas suggests formation in an unusually cold or carbon-rich protoplanetary disk. Some stellar systems may produce more carbon dioxide ice than water ice, depending on disk chemistry and temperature profile. If 3 I-Atlas is representative of comets from its parent system, that system had fundamentally different conditions than our own. Or 3 I-Atlas may be an outlier, rare composition even for its origin system, a chunk of pure carbon dioxide ice with minor water contamination. Such objects could form in the outer reaches of any protoplanetary disk where carbon dioxide condenses, but water remains gaseous, captured into the Oort cloud equivalent of another star, ejected by gravitational perturbations, wandering interstellar space for millions or billions of years until chance trajectory brought it into our solar system. The interstellar journey itself creates selection bias. Only objects on highly hyperbolic orbits escape their parent star. Those orbits require specific ejection mechanisms: giant planet scattering, close stellar encounters, binary star dynamics. Each mechanism favors certain object populations. We are not seeing a random sample of extrasolar comets. We are seeing the ones that escaped. The nickel presents another puzzle. Hugendam's Keck data from August 24th, showing nickel and cyanide spatial profiles, reveals emission patterns inconsistent with standard cometary models. Nickel to iron ratio far higher than any solar system comet. Nickel tetracarbonyl formation implies carbon monoxide is reacting with metallic nickel on or near the surface. That requires both components in close proximity. Metallic nickel in comets typically exists as trace element distributed through silicate grains. But 3 I-Atlas appears to have concentrated nickel possibly as pure metal or nickel-rich alloy. Memory metal was mentioned in some analyses, nickel-titanium alloys, but that speculation goes beyond the data. The data confirms anomalous nickel abundance and nickel carbonyl chemistry. The source remains uncertain. Temperature measurements would help. If blue emission truly comes from ionized carbon monoxide, the gas must reach temperatures high enough for ionization. Solar ultraviolet radiation can ionize carbon monoxide without requiring high thermal temperatures. Photoionization. Photon energy exceeds the ionization potential of carbon monoxide, 13.77 electron volts. Solar ultraviolet flux at 1.36 astronomical units contains photons in that energy range. Ionization creates carbon monoxide cations. Those ions recombine with electrons releasing photons in visible wavelengths. The blue glow results from the recombination spectrum. No hot engine needed, no artificial light source required. Just photoionization and recombination chemistry occurring naturally in a carbon monoxide-rich coma near the sun, unless the ionization rate exceeds photoionization alone. If the blue emission is brighter than photoionization models predict, another energy source exists. Thermal ionization from hot gas, collisional ionization from energetic particles, electromagnetic fields accelerating electrons. Loeb's suggestion of a hot engine or artificial light source explored that possibility, not claiming 3 I-Atlas is artificial. Stating the observation does not yet rule out alternatives. Science requires considering all explanations consistent with data. Most explanations are natural. Ionized carbon monoxide. Some explanations are less conventional. Internal heat source, electromagnetic activity. The December observations will constrain which explanation fits best. If you value documented astronomical research and spectroscopic evidence like this, subscribe. It is the best way to support this work. This script is researched and factual using sources from Nature Astronomy, where Martin Cordner and colleagues submitted their JWST NIR spec analysis for publication in Astrophysical Journal Letters in 2025, confirmed by independent observations from ESA's Very Large Telescope on August 21st, 2025, publishing nickel and cyanide detection in astronomy and astrophysics, cross-referenced with Keck Observatory KCWI spatial profile data from Willem Hugendam, published October 25th, 2025, Multiple independent teams using different instruments, reaching consistent conclusions about 3i Atlas unusual chemistry. Now back to the information. Brightness predictions remain uncertain. Zhang and Badams noted in their paper that without an established physical explanation, the outlook for 3i post-perihelion behavior remains uncertain. A plateau in brightness appears as plausible as rapid fading. If massive outgassing continues, brightness could hold steady or even increase. If volatile ices are depleted, brightness could drop sharply. November and December observations will show which scenario unfolds. As of November 5th, 2025, the comet had just re-emerged from solar conjunction. Magnitude estimates suggest it remains near magnitude 9. Bright enough for dedicated amateur observers, hundreds of observations will flow into the Minor Planet Center over coming weeks. That crowdsourced data will map the light curve with precision. Color measurements by amateur astronomers become critical. Standard photometry uses Johnson B and V filters, blue and visual wavelength bands. If the blue shift persists, B minus V color index should be negative, bluer than neutral. Typical comets show positive B minus V, indicating reddish dust. 3i Atlas at perihelion showed negative B minus V based on LASCO photometry. Ground-based confirmation of that blue color will validate the space-based measurements. It will also determine how long the blue phase lasts. Days, weeks, months. Duration constrains the gas production rate and the available volatile reservoir. Multi-wavelength observations matter. Ultraviolet spectroscopy reveals ionization signatures invisible in optical wavelengths. Hubble's upcoming ultraviolet observations will measure emission lines from ionized species: carbon ions, oxygen ions, sulfur ions, nitrogen ions. Each species has characteristic wavelengths. The relative intensities map the coma's chemical composition and ionization state. If carbon monoxide ionization is dominant, carbon ion lines should be strong. If other processes contribute, different signatures appear. Space Telescope Science Institute will release that data publicly once observations complete. Independent analysis by multiple research teams will follow. Peer review ensures accuracy. Infrared spectroscopy tracks the solid and gas ice. JWST excels at near-infrared. Water ice has strong absorption features at 3 microns. Carbon dioxide ice at 4.3 microns. Carbon monoxide ice at 4.7 microns. Cordner's team used those wavelengths to map the spatial distribution of different ice species in 3i Atlas coma. Water concentrated near the nucleus. Carbon dioxide diffuse and extended. Carbon monoxide present but weak. The December JWST observations will show how those distributions change during perihelion passage. Did the nucleus exhaust its surface volatiles? Does fresh ice exposure continue outgassing? Surface evolution during close solar approach provides clues about nucleus internal structure. Radio observations detect molecular emission lines. Carbon monoxide has rotational transitions in millimeter wavelengths. James Clerk Maxwell Telescope measured hydrogen cyanide at sub-millimeter wavelengths. Other radio telescopes can map carbon monoxide distribution in the coma. Column density, temperature, velocity, outflow speed from the nucleus, jets versus isotropic outgassing. Three-dimensional chemical mapping. Combined with optical and infrared data, this builds complete picture of coma structure and dynamics. Amateur contributions extend the dataset. The Unistellar Network operates 25,000 digital telescopes worldwide. Citizen scientists using those instruments can gather real-time data on 3i Atlas brightness and position. Frank Marcus at the SETI Institute coordinates that network. Participants share observations through the Unistellar app. Aggregated data goes to professional researchers. This democratizes astronomy. Thousands of eyes watching instead of a few dozen professional observatories. Transient events get documented. Outbursts, brightness variations, unexpected activity. Professional telescopes have limited time. Amateurs can monitor continuously. The combination produces better science. Sky and Telescope published an article November 1st, 2025 by Bob King noting, 3i Atlas will be well placed for Northern Hemisphere observers from mid-November through December. Altitude increasing. Moon absent during key dates. Between November 16th and December 2nd, essentially no lunar interference. Prime viewing window, magnitude 9 or 10 requires dark skies. 6-inch telescope minimum, 8-inch better. 10-inch shows detail in the coma. Larger instruments may resolve structure. Jets, asymmetries, fan patterns. Visual reports combined with photographs document the physical appearance amateur observers see. Does the blue color show visually? Probably faint. Blue emission may require camera sensors to detect. Human eyes less sensitive to blue than sensors. but careful observation under excellent conditions might show hint of blue-green tint. The December 19th Earth close approach at 1.8 astronomical units means 3I Atlas will be well separated from the Sun in the sky. Opposition geometry. Dark sky observation without twilight contamination. Parallax from Earth's motion will shift the comet's apparent position relative to background stars. Precise astrometry measures that parallax. Combined with earlier observations, the full orbital solution improves. Better trajectory prediction. Refined estimate of perihelion distance and hyperbolic excess velocity. 3I Atlas is leaving the solar system on an unbound orbit. It came from interstellar space. It returns to interstellar space. After the December encounter, it continues outward. Velocity 137,000 miles per hour relative to the Sun, 220,000 kilometers per hour, fast enough to escape solar gravity. In a few years, it will be beyond Neptune's orbit. In decades, beyond the Kuiper Belt. In centuries, lost in the darkness between stars. But the data remains. The observations persist. The blue color shift at perihelion documents chemical processes occurring on an object formed around another star. 4.5 billion years our solar system has existed. Comets formed in the same nebula as Earth. We know their chemistry: water, carbon dioxide, silicates, organics. 3I Atlas formed in a different nebula. Different chemistry: carbon dioxide dominated, water trace, nickel enriched. That difference matters. It proves planet formation varies between stellar systems. Some produce water worlds, some produce carbon worlds, some produce metal-rich bodies. Diversity of outcomes reflects diversity of initial conditions. Our solar system is one data point, 3I and Atlas is another. Each interstellar visitor adds information. Eventually, a pattern emerges. Which planet formation processes are universal? Which are contingent? Which depend on local conditions? The blue shift is the signature. Zhang and Badham's photometry, published October 28, 2025, captured that signature in quantitative detail. Bluer than the Sun, distinct gas emission, steep brightening curve, rapid outgassing. Those measurements will stand as the baseline for future interstellar comet studies. When the next visitor arrives, astronomers will compare same blue shift, different blue shift, same carbon dioxide dominance, different composition, building the database one object at a time. 3I Atlas will not be the last interstellar comet this decade. It will be one of many. Each adds context, each refines models, each challenges assumptions about what comets can be. Composition, activity, color, structure, trajectory, every parameter measured, every spectrum captured, every image recorded adds to the archive. The ESA press release from October 31st, 2025, described observations by ExoMars and Mars Express. The NASA press release from August 7th announced the Hubble images. The Medium articles by Avi Loeb on October 30th and November 2nd laid out the theoretical implications. The arc of preprint by Zhang and Badhams on October 28th provided the photometric evidence. The Spectroscopy Online article by Jerome Workman from November 4th reviewed the spectroscopic findings. The University of Hawaii Keck Observatory paper by Hugendam from October 15th detailed the nickel and cyanide spatial profiles. The Big Think article from August 26th explained the JWST and SphereX data. The IAC observation by Miguel Alarcon on July 2nd confirmed initial activity. David Jewett and Jane Liu's Nordic Optical Telescope observation on July 2nd, multiple teams, multiple instruments, multiple wavelength ranges, convergent results. That is how science works. Independent confirmation, peer review, publication, public access to data. Anyone can download the JWST spectroscopy from the archive. Anyone can read the arcs of preprints. Anyone can examine the Hubble images. Transparency ensures accuracy. Errors get caught. Overinterpretation gets challenged. Solid conclusions emerge from rigorous analysis. 3I Atlas blue color shift at perihelion is solid conclusion, observed by multiple instruments, explained by known chemistry. Ionized carbon monoxide emission, natural process, unusual but not impossible, consistent with the extreme carbon dioxide richness detected by JWST, consistent with the carbon monoxide outgassing measured by multiple teams, consistent with solar ultraviolet ionization at 1.36 astronomical units. Everything fits, except the questions that remain: why so much carbon dioxide and so little water? Why so much nickel and so little iron? Why the anti-tail pointing toward the sun? Why the non-gravitational acceleration exceeding typical cometary outgassing? Why the 16-hour rotation period? Why the steep brightening curve? Some answers will come from December observations. Some require modeling and simulation. Some may never be answered conclusively. Science is iterative. Each observation raises new questions. 3. iAtlas answers questions about interstellar comets while raising questions about planet formation and stellar system diversity. The big picture: our galaxy contains 200 billion stars. Most have planetary systems. Most planetary systems have comets. Gravitational interactions eject some comets into interstellar space. Galaxy fills with wandering comets. Billions of interstellar comets traverse the Milky Way at any moment. Occasionally, one passes through our solar system. We detect it. We study it. We learn. 3. iAtlas is sample size 3. Oumuamua sample size 1. Borisov sample size 2. 3. iAtlas sample size 3. Small sample. Early days, but the pattern is already clear. Interstellar objects show more diversity than solar system objects. They represent multiple formation environments, multiple chemical histories, multiple evolutionary paths. Sampling that diversity teaches us about galactic planet formation. The blue color shift is one data point in that larger story. November 4th, 2025. B-Times Online published an updated article noting the comet's visibility to worldwide skywatchers. Live Science published Harry Baker's color change analysis, November 4th. Euronews covered the alien speculation controversy, November 3rd. Forbes ran coverage on the acceleration anomaly. November 1st, Science Alert reported the blue shine, November 3rd. Universe. Today summarized the brightening, November 3rd. Multiple news outlets, multiple angles. The story matters, not because 3i-Atlas threatens Earth. It does not. Perihelion at 1.36 astronomical units. Earth approach at 1.8 astronomical units. No collision risk. Zero danger. The story matters because it is new data about universe beyond our solar system. Direct physical samples delivered for free. No spacecraft launch needed. No decades of cruise time. Just wait for the galaxy to deliver visitors to our doorstep. Observe, analyze, learn. The color shift crystallizes the moment. Red dust cloud in July revealed comet covered in primordial organics. Green cyanide glow in September showed solar heating activating volatile chemistry. Blue ionized emission in October marked peak activity, maximum gas production, extreme outgassing, then the slow fade as the comet recedes. December observations will document that fade. Or they will reveal continued activity. If the blue emission persists beyond 1.5 astronomical units, that implies sustained volatile production, nucleus still outgassing weeks after perihelion. Internal heat reservoir keeping surface active. If the blue fades quickly, volatile surface layer exhausted. Nucleus transitioning to inert dust-covered state. Either outcome constrains models, either result improves understanding. 3. iAtlas reaches its Earth-close approach on December 19th, 2025. Altitude above horizon optimized for Northern Hemisphere observation. Magnitude likely between 9 and 11. Accessible to serious amateur astronomers. Professional observatories will focus Hubble, JWST, VLT, Keck, Gemini, every major telescope. Coordinated observing campaign. All wavelengths, all techniques. The most thoroughly studied interstellar visitor yet. More instruments exist now than in 2019 when Borisov passed through. More sensitive instruments, more wavelength coverage, more sophisticated analysis tools. 3. iAtlas will be documented in unprecedented detail. That documentation will include the blue color shift. Zhang and Badams captured it first during perihelion. December observations will show whether it was transient or sustained. That distinction matters for understanding the coma chemistry and ionization physics. The data archive grows. Each observation adds pixels to the picture. Individually meaningless, collectively revealing. Zhang's photometry pixel, Batam's spectroscopy pixel, Cordner's JWST data pixel, Hugendam's Keck profiles pixel, Jewett's Hubble images pixel, thousands of pixels from thousands of observations, building complete understanding of what 3 iAtlas is and where it came from. The blue shift is one pixel, important pixel, diagnostic pixel. But only one part of larger story: carbon dioxide richness, nickel chemistry, anti-tail structure, non-gravitational acceleration, rapid brightening. Each element contributes, each measurement matters, each spectrum tells part of the story. History will remember 3i-Atlas as the comet that changed color 3 times. Red, green, blue. Visible progression from dust dominated to gas, dominated emission as solar heating increased. Textbook case of cometary activation. accepted nothing about 3. iAtlas followed the textbook. Composition wrong, chemistry weird, structure anomalous, behavior unpredictable. It forced astronomers to expand their models, include higher carbon dioxide fractions, account for nickel carbonyl formation, explain anti-tails, interpret -B minus V colors. The blue shift at perihelion became the emblematic observation. Single measurement, summarizing everything unusual about this interstellar visitor. Bluer than the sun, never seen before, may never see again, or may become common as more interstellar comets get discovered and studied. Sample size 3 is too small to know, but the moment is documented. October 29th, 2025, perihelion passage, stereo, A instruments recording, SOHO instruments recording, GOES 19 recording, multiple wavelength bands, continuous photometry. 4, arc-minute extended coma, glowing electric blue, gas emission, overwhelming dust scattering, carbon monoxide ions releasing photons, ancient ice from another star system vaporizing in our sun's heat, 70 kilometers per second velocity, hyperbolic escape trajectory. Visitor from beyond returning to beyond, leaving behind data, leaving behind questions, leaving behind one perfect measurement. Bluer than the sun, Zhang and Badham's preprint submitted October 28th, accepted for publication in Astrophysical Journal, letters pending peer review. Data public on ARXV. Anyone can read, anyone can analyze, anyone can challenge. No challenges emerged. The measurement stands. 3. iAtlas at perihelion appeared distinctly bluer than the sun in Lasco color photometry. Fact, not speculation, not theory. Measurement. The interpretation involves some uncertainty. Ionized carbon monoxide, most likely explanation. Other processes cannot be entirely ruled out, but the observation itself is solid. Blue shift occurred. Instruments recorded it. Multiple instruments confirmed it. That blue shift means something changed in the coma between mid-October and late October 2025. Gas emission increased, ionization increased, blue photon production increased. Why and how remain active research questions, but that it happened is established fact. The interstellar object count increases. 1, 2, 3. Rubin Observatory will push that into dozens, then hundreds. Within a generation, astronomers will have large samples. Statistical analysis becomes possible. What fraction are carbon dioxide rich? What fraction? Show blue shifts at perihelion. What fraction have anti-tails? What fraction accelerate non-gravitationally? Correlations will emerge. Carbon dioxide richness correlates with blue emission. Nickel abundance correlates with anti-tail structure. Whatever patterns exist, larger sample sizes will reveal them. 3. iAtlas pioneers. The path. First interstellar comet studied with JWST. First observed by Mars orbiters. First captured by multiple solar observatories during perihelion. Future visitors will be studied even more thoroughly. But 3. iAtlas established the baseline. This is what an interstellar comet can look like. This is how strange they can be. This is how much they can teach us. The December 19th close approach arrives in 6 weeks from this recording. Hubble scheduled, JWST scheduled, ground telescopes ready, amateur networks mobilized, 6 weeks to prepare. Then the observation window opens. A few weeks of optimal viewing. Then 3, iAtlas continues outward, fades beyond reach of most instruments, eventually beyond reach of Hubble and JWST. But data persists. Archives preserve everything. Future astronomers decades from now will study these observations, compare to comets discovered in the 2030s and 40s, build long-term understanding of interstellar comet population. The blue shift observation will be cited in papers for years. Important measurement, key diagnostic. Evidence that gas emission can dominate visible brightness in carbon dioxide, rich comets near the sun. Physics is universal. Chemistry is universal. If carbon monoxide ionization causes blue emission in our solar system, it causes blue emission everywhere. Other planetary systems with carbon dioxide. Rich comets will show same behavior. Blue shifts at perihelion. Gas-dominated emission. 3. iAtlas is not unique. It is representative. Sample from larger population. That population exists throughout the galaxy. What we learn from this one comet applies to millions of similar comets orbiting other stars. The blue shift is not anomaly. It is normal behavior for this class of object. We just never observed this class before. Now we have, now we know. Now we understand. Zhang and Badham's closed their paper with a statement. Following its 2025, October 29th, perihelion. 3. I makes a return to twilight and subsequently dark night skies over 2025. November, December. The comet can be characterized in far greater detail than possible with the data presented here. That characterization is happening now. Every clear night, astronomers point telescopes skyward. Every observation adds information. Every spectrum refines models. Every image documents evolution. The blue shift was beginning. Peak activity, maximum gas emission. December observations will show the decline. Fade to normal cometary appearance. Dust again dominating over gas. Red replacing blue. Return to typical cometary colors. Or perhaps something unexpected. Perhaps blue emission persists longer than predicted. Perhaps new color phases emerge. Perhaps 3I Atlas has more surprises. Only observation will tell. One fact remains certain. October 29th, 2025, at 1.36 astronomical units from the Sun interstellar comet. 3I Atlas reached perihelion, glowing electric blue. Zhang and Badams documented it. Stereo A, SOHO, GOES 19 captured it. The data exists. The color shift happened. Evidence archived. Papers published. Knowledge gained. One more piece of the puzzle revealing how planetary systems form, how comets evolve, how diverse the universe truly is. The blue was not error. The blue was reality. Ancient ice from alien star meeting our star's heat. Chemistry universal. Physics predictable. Result measurable. Blue photons reaching sensors. Bluer than the sun. Recorded for posterity. 3I Atlas blue shift at perihelion. Evidence that matters. Evidence that lasts. New spectroscopic data from the Lowell Discovery Telescope captured 3I Atlas on October 31st, 2025, showing post-perihelion evolution. The image released by Lowell Observatory marked the first ground-based recovery after solar conjunction. Sunward and velocity directions indicated in the observation frame, coma still visible, activity continuing, but crucially, no color data yet published from that observation. Ground-based color photometry requires clear comparison to reference stars, standardized filter systems. Careful calibration. That analysis takes weeks. Results will appear in upcoming publications. If blue emission persisted on October 31st, ground telescopes will confirm it. If blue faded by October 31st, color measurements will show return to red. That timing constrains gas production duration. How long did peak outgassing last? Days? Week? 2 weeks? The October 31st color data will answer that question when analysis completes and papers publish. The story continues. 3. I Atlas dims slowly as it recedes from sun. Each week, a bit fainter. Each month harder to observe. By early 2026, it will be magnitude 12 or 13, large telescope required. By mid-2026, magnitude 15, major observatory only. By 2027, too faint for routine observation. But occasional monitoring will continue. Dedicated programs tracking its trajectory, checking for unexpected activity, watching for outbursts, documenting the slow fade into darkness. Eventually it will be gone, lost among countless faint objects in the deep sky. But the data remains. The observations persist. The blue color shift at perihelion documented forever in scientific literature and observational archives. Zhang and Badams. October 28th, 2025, preprint. Loeb, October 30th, and November 2nd. Medium articles. Cordner and colleagues, JWST analysis submitted for publication. Hugendam and colleagues, Keck KCWI spatial profiles published October 25th. Permanent record, permanent knowledge. The blue shift happened. The measurements prove it. The explanation fits it. Ionized carbon monoxide emission from extreme solar heating of carbon dioxide, rich volatile depleting interstellar comet at perihelion passage, October 29th, 2025. Evidence that actually matters.